Now, let's we discuss a little bit further on our discussion on the motion in the ocean. While we talk about the ocean currents, right? We already discussed about the waves, now on the currents. As we all know, the water column in the ocean is constantly moving. Theoretically, you won't see anywhere in the ocean like a standstill. Though we call sometimes it's calm waters, it doesn't really mean they are really calm. Still, you will see some sort of a movement to one way or the other, on any direction. Right? So this movement will affect by the climate and many local conditions, and also that affecting the humans and also all the organisms, right? So what are these currents? Then the waves actually, they are, as you know, they are not really moving the water column, but it's the energy. But the difference here is the ocean currents. They move, right? It's a sort of a directed movement, some sort of directed movement of the water column. Right? They can be like rivers, as you can see in the bottom in some of the images. Right? These currents actually like rivers in the terrestrial environment. Like they have some sort of a direction, as well like it's a flowing water body, same as a river. Right? And they can like affect the sea bottom and the water column, because they are like dragging anything in the coming under the or around this stream, right? So it's just same as a river. Now these currents can be either in the surface, right? Then, right, and even you can see this kind of currents even the depths, right? And on the other hand, these currents can be like in the short distances, whereas sometimes it can be longer distances, whereas some of the currents can run in entire ocean, right? Just one wave or a current can go across the whole earth, especially something like the tide. So imagine, like it can be from short to mid-range to even the whole globe. The huge differences in the currents, right? So as I mentioned, there are two different types of currents: the surface currents and the subsurface currents, or deep current. Right? There are more deep currents actually than the surface current. As is 10% of the currents are actually in the surface actually, but much or the most of the currents are actually in the ocean bottom. We call it subsurface or the deep water currents. Again, same as the waves, the one of the main reason behind the currents is also the wind. The wind is the primary source for the current, and the other driver is actually the density differences, as you can see. So density differences can result in the movement of water column. Right? So the wind density differences, as well as some other the forces, something like the gravity, particularly play a key role in the movement. Then the other concepts that we already know, something like the Coriolis effect and the like thermal expansion. Like we know that the unequal heating on Earth, especially when the sun's rays hitting the straight or in an angle, depend on that. Likewise, there are so many factors affecting the currents. Right. So at least there are the surface currents and the deep currents. So the main forces then among them, the main forces for the ocean currents are actually the main drivers, actually the thermal expansion. That's something that we discussed previously. As you know already, when we call the overhead sun, like when the sun is overhead, or when the rays are coming on a right angle, like it in the tropical ocean, like this area get the most of the heat. But at the same time, we know that this move up and down in between this few degrees. Right? So the temperature will be higher either in the equator or a little bit above or below, like based on the position of the sun. But anyway, the tropical region get the most of the heat, and because of that, with the heat, that area will like expand a little bit, thermal expansion, which, as you can see in a side by side view in this here. So will be a small degree of expansion in the tropical areas or in the equator, and that will result in movement in the water column, like in a downhill, right? Don't expect like it can be a couple of meters, sometimes high in the tropics than the other polar region, and that will result in the water movement because of this thermal expansion, right? But that's something considerable effect here, right? And this thermal expansion is one of the reasons for this the ocean currents, right? This can cause huge currents that will be running from the tropics towards the either side of the globe, like from here to there and from into there, right? So that is thermal expansion. Now the other thing is the wind, the impact of wind. We have already discussed a little bit on the wind. So because of the thermal, like differences in the temperature in different regions, right, you will have the low pressure zones and the high pressure zones, and this kind of hard shells on Earth we discussed already, and these things will cause the atmospheric circulation, like these thermal differences will cause, like in the high temperature, then the air will be thinner, where it will go higher, whereas in the lower pressure they will come down, like making some sort of shells like this. Now, if you look at very closely on this, the Earth, you can see the direction of wind flow is different in layer by layer. Like in the if you look at the equator, either side of the equator, you see there is a wind coming from this direction, sort of a northeast direction, right? It's coming from northeast direction, like here, and below the equator, you see it's a southeast direction. It's coming from southeast towards here, and this is from northeast to that direction. And here, you see after 30 degrees, you see another airflow. It's more from western to eastern side. These are from east to west, whereas these are from west to east. And again in the polar region, you see again from east to west. And the direction of the wind flow is different from region to region. So it is because of its flowing from the east to west, they are called easterly or polar flow, right? Or polar winds. They are actually easterlies because they are flowing from east. It's called the polar easterly winds. Right? Again, you are hearing this for the first time, you might get confused, but just their name, the winds are named based on whom they are blowing from. Like if they are blowing from the east, we call the easterly. Right? Since they are in the polar region, then we call polar easterlies. Right? Then this subpolar region, they are flowing from west to east, so they are called the subpolar westerlies because they are flowing from west. And in the middle region, that's in the latitude, so in the equator, you will see there are northeast uh, winds. They are more actually easterly winds, but these have a different names called trade winds. Right? Trade wind, the northeast trade winds or just trade wind. I'm not too sure if you have heard about this something called the trade winds, but in local terms we call Velanda Sula. Trade wind, why they call trade wind? Because during the history, especially the sailors, they use this wind for sailing, especially the traders. Some several years back, especially the Arabic and Chinese and other the traders who were going from continent to continent, from country to country, they make use of this the wind for their movement, especially for the trading purpose. So because of that, they are called trade wind or Venezuela. Right? So I hope you got some idea. At least you just need to know that the direction of wind is different from different layers or different regions on Earth. Some are easterly winds, some are westerly winds. So at least if you know this thing, this is enough for the moment. And you can see this wind causing different shells or patterns on Earth, right? They are causing this kind of different shells, uh, Hadley shells, right? And they result in, and this also impact on the ocean as well, right? So how does it affect? As you can see here in the next diagrams, uh, this what we call the trade wind. You can see the trade wind from anything below the equator, they are pushing towards the equator, right? Even from the top, like in the above the equator, they again from the uh, northeastern direction, they are pushing again to the equator. From both sides, above the equator and below the equator, they are pushing the water column towards the equator, right? So that makes a sort of a bulge, or like previously that the water column will be accumulated here in the mid because it's pushing from the both sides. Hope you can understand, right? The water column like this, when they are pushing for the either side, so that can like raise the water column a bit, right? And similarly, you remember that the westerly winds also pushing towards the polar region, and the top polar uh, easterlies, they push into the other side. And in the subpolar region also, they will have this kind of a situation, like the water column is pushing. Right now, when the water column push from the both side, and that will ended up in some sort of a hill formation. And now again, that water column they won't stand like this, and they start flowing back, making some currents, right? So that's how, other than the thermal expansion, this wind create some push in the water column and also making some Sokombu current. Now you can see this thermal expansion together with wind, they are acting together. And so the thermal expansion and the wind, especially the trade wind and westerly wind, right? They are putting a lot of pressure or a lot of force for the ocean to make this ocean current, right? I know you might not get a clear idea on this. I will explain a little bit further later if you don't understand, but at least you just need to know that the wind pushing in different direction in the water column as well as thermal expansion will create some water to move, right? And especially in the equator, the trade wind is the main force actually. The trade wind is the main force pushing this water column together with the one we discussed as the thermal expansion, because the thermal expansion is highest in the equator because its temperature is highest there, and the wind pushing in the both sides as well and making like a huge bulge in the water surface, and that will create the water column movement, because the water won't stay like this in an angle and it start flowing back across down the hill, making some currents. Right? So this is one way of the ocean currents can be generated, right? Again, we have a small video. Just watch that one and we'll discuss it further.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive in these swirling seas? Take a closer look at some truly fascinating ocean dwellers with these two animations.
Okay, I think that video gave you a sort of an overview about the ocean currents, right? As you would understand, so complicated. Right? So that's why this subject is mostly like a physics-based subject, not for biologists, but we are just trying to understand the basic concept of the ocean currents, right? Anything beyond is about the modeling, and you need to explain things from the physics, like even the wave formation, all these things you can explain using the physics. But we just need to understand the very basic concepts, and especially then we will link this to how the ocean currents wave they affect the biology for the organism, right? So that video actually puts some sort of foundation and to the course, and we will continue our discussion on the ocean currents when we meet next time. So that's all for the day.